Hello everyone. As part of learning generative AI, we were looking at what are the key components of GAN, generative adversarial networks. Today we shall see how do we go for training of GAN while building the model. So whenever you are working with GAN, it consists of, we know by this time, GAN consists of two types of neural networks. One is the generator, the other one is the discriminator or the evaluator. What is the major functionality of the generator? It has to generate new data. We are also calling it as synthetic data. Whereas the discriminator, what is the major functionality of the discriminator? It has to distinguish between the real data and the fake data. The discriminator always strives to find out whether the generated data is real or fake. So the training of GAN involves the following key steps. First one, how do we train the generator? The generator always tries to learn from the existing data set, and it tries to learn how to create realistic data which is almost close to the existing real data, and it tries to learn from the introduction of random noise into the data, and it is trying to maximize the fooling ability of the discriminator. It always tries to fool the discriminator. So as a generator, my job is to create more realistic data wherein I am trying to fool the discriminator to distinguish between real and fake data, right? So the training is done by introducing the random noise, and you are trying to learn from that and create more realistic data. Discriminator training, the discriminator is trained to correctly classify the real data from the synthetic data, right? The goal is to minimize the classification errors, and it has to always try to identify the differences between the real data and the data which is generated by the generator. Coming to the adversarial process, this is the most important part of a GAN, which is trying to build the kind of competition between the generator and the discriminator. This one will try to work like a zero-sum game, wherein the generator always try to improve. Generator improvement means it is trying to create more realistic data, and the discriminator improvement is it is trying to be better at distinguish between the real and fake data. Loss functions, there are two types of loss functions, one towards the generator, the other one towards the discriminator. Generator loss function always tries to minimize the difference between the existing data and the generated data, whereas the discriminator tries to maximize the accuracy of the classification algorithm, because it wants to prove whatever data that is being generated is real or fake, right? So the discriminator always tries to maximize the classification algorithm, and it will try to prove more accurate classification. Coming to the challenges, sometimes GANs training can be unstable and it can be prone to some kind of errors. What kind of errors? Like mode collapse. What do you mean by mode collapse? The generator might try to provide only limited variations. It may not give you more number of variations while generating the data. And non-convergence. What do we mean by non-convergence? The data that has been generated may not converge towards the realistic data. So in such cases, we try to go for various types of normalization techniques which will try to address these issues. Now GAN training will be effective when we are trying to balance the generator and discriminator performance, and also we try to see none of them is overwhelming the other one with the realistic synthetic data over time. Coming to the next type of network model, which is VAE, stands for variational autoencoders. These are also a type of generative AI model which will try to represent the data in a lower dimensional latent space. It is like, it works like one encoder will be there, one decoder will be there. I can take an example of image size compression. Sometimes whenever you are applying for any kind of examination, they say the image size should be only this much. They specify the size of the image. In such cases, when you want to compress the image, still it should look like the original picture, we can go for working with VAEs, variational autoencoders. So first what it will do is, the encoder will try to take the original image, will try to put it in a compressed format, or it will try to compress the original data and stores it in a distribution space. Then the decoder will take the data which is written onto the distribution space and reconstruct the image. Thereby the decoder's output looks similar to the output, the input which was given to the autoencoder, right. So the encoder decoder structure, what is the encoder trying to do? The encoder maps the input data. Generally, he takes example as an image into a latent space represented as a probability distribution. We use some probability distribution algorithms, and we will try to map the original input data into a latent space with probabilistic distributions. And what it will do, instead of directly outputting latent variables, the encoder outputs the parameters of the distribution such as mean and variance. What the decoder will do, it will try to take a sample from the latent distribution and tries to reconstruct the image again. So you can go through this variational autoencoders in the context of image compression, right. So two types of uh, components will be working. One will try to take the input image, I am taking example of image compression. One will try to take the original image and try to see what are all the things that can be avoided in order to reduce the size of the image, yet it should resemble the original one. It will try to write the compression details onto a latent space. The decoder will try to read that data which is output of the encoder and will try to reconstruct the image which resembles the original one, still avoiding some data which will try to increase the size of the image. Latent space, it is the compressed representation of the input data, and the variational autoencoders are trying to make sure that this space is continuous. It is containing continuous information than the discrete kind of information, and it is also of smooth structure wherein the interpolation of the points becomes easy for the decoder. And this is different from the traditional autoencoders which have disjoint or discrete latent spaces. Then what is variational inference? Whenever we are trying to work with the variational autoencoders, they are trying to work with the variational inference which will try to approximate the true posterior distribution. What do you mean by posterior distribution? Whatever we are trying to take output from the autoencoder, I am trying to write it into a distribution space wherein I am not losing the original data. At the same time, I am trying to avoid the unnecessary details and trying to give a continuous distribution of the input data. And this variational space consists of two terms. One is the reconstruction loss, the other one is the KL divergence. What do you mean by reconstruction loss? How best the decoder can reconstruct the image. So whenever you are trying to say the decoder is reconstructing the image, how best it can reconstruct the original image, so that say for example, I have taken my passport size photograph which is of 8 MB, say for example, and the application process wherein I am applying, it says you need to upload your image of size only 2 MB. So I need to avoid 6 MB of the data from the image, and I should create a 2 MB size of the same passport size photo, which should look like my photo only, right? Because I am applying for that. So how do I go for? How the decoder is able to reconstruct the image with lesser size? That comes under reconstruction loss. This will be implemented generally as mean squared error or binary cross entropy. These are the statistical measures which will try to help us to determine the reconstruction loss. Then KL divergence, what it will try to do is, it will try to measure the difference between the encoder's output and the original data distribution. The encoder is trying to write the data onto a distribution space. So this KL divergence will try to see the difference between the actual data distribution and the output from the encoder's distribution. It will try to measure the difference between them. And this one will ensure that the latent space is always remaining continuous and smooth, wherein the decoder can proceed with its functionality. Sampling and reparameterization, in order to work with the gradient based optimization feasible. These are all the optimization measures wherein how best the encoder and decoder are working. This uses a reparameterization trick. What it is trying to do is, instead of sampling directly from the latent distribution, it tries to sample from standard normal distribution and then shifts it and scales it to the original image construction. What is the meaning of this one? Instead of directly taking it from the latent distribution, it will try to take some sample distribution points from the latent space and then reconstructs the image. Then it will try to see what is the required size of the compressed image, then scales it accordingly to the size that is required. In such cases, sometimes we might go for back propagation and sampling mechanism iteratively. Then finally, the generative process. After the model is trained, the new data can be generated from the sampling points which the decoder has identified in the latent space. And the decoder will try to obtain realistic data, and it will try to see a balance between reconstruction accuracy and regularization, wherein you are not losing the originality of the data that you have taken, at the same time trying to generate new data from the original data which is meeting the requirements of the application. Thank you.